So thanks everyone for coming today. Thanks Cans for having a whole room to join in on. So I wanted this talk because I wanted to do this talk because I felt like I have stuff to contribute in terms of statistics, but there's a whole course in Townsville called the Murray-Logan stats course. And I felt like I couldn't really like step on Murray-Logan's feet at all because he already does a whole like stuff on Bayesian stuff. So I didn't feel like I could cover anything too statistics related. So this talk is kind of a bit in between. It's more like conceptual. So if I think a couple of people in the audience are already pretty familiar with this stuff, but for a lot of us, it'll be pretty new. It's about kind of deciding on causality in your statistical models. So statistics only goes so far. It's one tool, but you really need to understand what you're doing with it. Otherwise, you might be doing kind of bad things with statistics. So I think it's really important to understand causality, or at least try and at least guess at what causality is whenever we do science. Especially when we don't have any way to control variables. So this is especially important in like observational studies, or if we're just pulling random individuals out of a population and not, putting them through any kind of treatment pressure or anything like that. So this is where causality is really important, and why including more variables can make your inferences a lot worse. It is possible. And I'd just like to also note that this whole presentation is basically, it's not stolen, but it's very largely inspired. And some of the examples are entirely taken from Richard McElrath's stuff. So he's kind of he's like my idol on this subject, but there's also a lot of other people and books out there as well. But I'll give you a link for his YouTube channel at the end. But again, a lot of his stuff comes from his talks, and I'm just trying to really condense it and make it into an hour-long session if I can. So just before I get started, I just like to acknowledge the Wilguru Kappa and Bindo people's land in which we're on today. I'd like to pay my respects to all elders, past, present, and emerging. So with that, I've kind of divided into chapters, 3 chapters, and the first chapter is acceptance. So just keep that in mind for now. There's a few examples that are being kind of our motivating examples today. The first one is just a data set that is on sleep. So basically we have kind of 3 variables in this data set. We've got sleep, alertness level, and then a student's test result during the day. So we basically just went out, sampled a bunch of students, and then we already standardized these. That's why they look weird. But basically we've got standardized sleep, alertness, and test results. And now our initial hypothesis would probably be something like, well, I bet you sleep obviously affects test result, right? And probably alertness too. So your initial idea might be correct in that sleep level might be related to test result. And we might go in thinking, okay, well, let's do the stats on it. Let's run the stats, and we make a model. And our model is, I didn't include it here, but it's got sleep and alertness predicting test results. And you might do this, and this might be, secondhand nature. We just plug them in, plug in all the variables we have. And it's something very common that we all do. And what you'll find is that there's a really strong effect of alertness and almost completely negligible effect of sleep. Amazingly, sleep has no effect in this data set on the statistics tests that the student's taking. So what the heck's going on? Sleep, not important apparently. So there's something, in your mind that's probably going off, and you're saying something's wrong. Like there's obviously something wrong with the way we've done this, and that's good. If that alarm bell is going off, you're on the right track. There is something wrong in this, and we'll get to it in just a second. So alertness clearly has an effect, but sleep level does not if we analyze it this way. Now, another example would be something like, do basketball players, does their height affect their scoring ability? And this is a really common example. I'm stealing it off of the YouTube channel, as well as a Twitter by Matthew Han, third reviewer on Twitter. And he basically analyzed this data set and he made a plot of it. And essentially there is no relationship. There is really nothing going on between an NBA player's height and scoring ability. It doesn't matter how tall they are, they still score about the same. If we put I don't have the line on it, but if we put a line through it, it would basically be a flat slope, no relationship. And this is kind of surprising, right? Like, basketball players, they need to be tall to play the game. So how is this possible that there's no relationship between height and scoring? And so this, again, probably ringing some alarm bells in you, and that's a good thing. Now, these are kind of the easier examples, and we're gonna analyze them in just a sec, the way that Richard McElrath. Oh, sorry. So one thing I might have to do in this talk is restart it, because sometimes it freezes. It just has like memory overload. Can everyone see that again? Okay, cool. Yeah. So a third example would be, and this is actually also shown in like many studies has been found. Does your grandparents' education level affect your own? So whatever level of education your grandparents obtained, I've just marked them here, grandparents as G. You've also got your parents' education level as P, and a child's education level that they later on attain throughout life. And basically, we want to know, how does your grandparents, what's their direct effect on the children in this data set? We've got a complete data set of grandparents, parents, and children. Again, standardized data, so don't worry about the numbers in that data set. But the first thing you might be thinking is, okay, if I was going to model this, I would probably do children as the Y variable, and then by grandparents and maybe parents as well. So you can include either ones. So let's just see what this looks like if we try and do this with this data. So if we just looked at grandparent alone, we'd see a pretty strong positive effect, well, fairly strong positive effects on the child's education level. And this kind of makes sense to us. Like, okay, obviously grandparents, if they had a higher education level, they're probably going to imprint that on their children. But now let's look at the same exact model, but we add in parents as well as another covariate. If we do this, we see, again, a strong effect. And I've actually had an interaction here, but the interaction is not significant. But if you see on the bottom, the effect of the interaction, nothing really there. But grandparent and parent, strongly significant as parameters. But we see that parents have a positive effect on children's education level. Grandparents have a very strong, fairly strong, even stronger than before, positively negative effect. So grandparents, if you have a more educated grandparent, you're more likely to be a lower education level. You're basically, it's negatively correlated. So this is very crazy, but this is actually seen in studies that if you just naively analyze it, grandparents can have a negative effect on their grandchildren's abilities, but only if you include that parent effect. If you don't include that parent effect, it's positive. Now, what if I told you that this data set that I have here is actually grandparents don't have any effect? There is zero effect of grandparents, but no matter which way you analyze it, you're either getting positive or negative. And I've made it so that grandparents have no effect on the children, no direct effect. So this is kind of crazy that we can get two completely wrong results, opposite directions on children. And what the heck is going on? How can we fix this? This is a huge thing. And we would never know, because I simulate the data, but we would never know otherwise that it's wrong. So how can we get at this? What tools do we have to kind of analyze this? I'm doing pretty good for time already. I might finish this pretty quickly. So I'm just gonna let you kind of ponder on this hard example. This is really a crazy one that, like, we can see it here. If we, the different echelons, I should say, on this graph are basically just, if we just grouped parents into bins, and then we did like kind of regressions through that, we can see that there's negative slopes for each of them. So parents clearly have a positive effect, in higher parent education level, positive effect, grandparents, negative effect. Should we all, hope for non-educated grandparents so that we're, attain a higher education level? I don't think so. I don't think that's logical, but maybe we can go through some steps to analyze this. So I guess the first step that I'm always saying is we have a problem, and the first step is acceptance. So I hope you'll join me. I already had this shirt made, not for this presentation, but it's we're all in the Analytics Anonymous Club. We're all in the AA of data analysis. Nobody talks about this stuff. It's going to be super important, though, in the future, I think, about understanding that there's issues with the way we analyze data. We can't just throw stuff in anymore. We really have to think about it in science. And I think it's starting the ball rolling, but we really don't understand it yet. We have to start really thinking about which variables we include and really, taking steps to address this. And so what Richard McElrath really recommends is something called a DAG, and we'll get into it in just a sec. But chapter 2 is all about embracing alchemy. I'll get to what that means. Oh, shoot. I'm just going to restart it again. All right. So there are confounds everywhere within biology. And here I've just labeled a confound as a U, and they basically can affect our relationship between X and Y. So in this relationship, for instance, this unknown confound is affecting X, and it's also affecting Y in some way. And this obscures the relationship between X and Y, whereas you can't see what's going on when you have this U in the equation, just by having it. So there's confounds everywhere in biology. They're literally everywhere. We really have to consider them quite widely. And one thing that can really help is trying to make these directed acyclic graphs. So what does this mean? Well, directed just means that it's one-way arrows. So we're usually inferring that something's causing something else and not the other way around. One way we can get at this is like if something happens beforehand and it's likely to be the cause, we can often infer to that, although there is a fallacy there. But basically, we're trying to infer some direction to it and not have any two-way arrows. The acyclic part comes from the fact that it's not looping. We can't have like an ever looping thing. That won't work in these causal diagrams. You always has to be like, the end goal. And remember, there can be a lot of these different confounds. There doesn't have to be just one U. There can be U's affecting things. Otherwise, there can be things affecting U and going through U to affect Y as well. But as long as we have these extra paths, it's going to be an issue. And then graph, of course, is a late 19th century abbreviation of graphical format. I just added that in. But my point with this is just that we have to look at these paths. There's something called a backdoor path. And basically, it's any path that goes from X to Y that goes through other variables. And basically, because of that, it's going to have a lot of messy information that we need to control for, or sometimes we don't need to control for. It all depends. So we got to really worry about these paths. So whenever we're doing these DAGs, we basically make a diagram of everything that can affect everything that we think of, and try and think of all the paths that can go from our main variable, explanatory variable X, explaining our predictor variable Y. And we should always try and do this in science and strive for making some kind of DAG or directed acyclical graph whenever we do an experiment. And the nice thing is that a lot of times good experimental design can help control for these confounds. So we can really control for them through randomization. So the effect of a confound might not be possible if we randomize by treatment and stuff like that. Independence, replication, blocking, and controls all really kind of help with this. So we've already invented, ways of doing this already. It's just when we come to like field studies where this is no longer extremely possible, that's where we really have to start worrying about causality and what's causing what. So if you have a really controlled experimental design, I'm not saying you have to use you don't have to worry too much about unknown confounds. I mean, you do obviously, but you're already addressing them in some ways. So using controls and things like that can also help address confounds. So I'm not going to get into experimental design today, but I'm just telling you, in the case where we don't have this, and obviously it's eliminating that path when we have these things. It's essentially disintegrating that path through U, and then we just have the direct effect of X on Y when we do these kind of things. Now, the issue arises when we don't have any idea about how to control this. So for instance, field studies, large observational studies, we often don't have any manipulation in these studies. We're just going out and we're surveying things that are already there. And that's where causality roams free. We have all these unknown paths that we can't control for. So where we can't manipulate, we need to use causal alchemy, as Richard McElrath puts it. I did not invent this. This is all Richard McElrath. So there's kind of 4 main rules that you should know about. There's the fork, the pipe, the collider, and the descendant. And we'll be going through each one eventually throughout this. And these will really be like the way you analyze everything. So basically, we just look for patterns. So the fork, for instance, is like we just saw. It's where we've got something in the middle affecting 2 other variables. That's the fork. So this U is actually a fork right now. So let's actually get to this. Oops, is this going to go away? No. I'll just restart quick. I hope it doesn't do that every time. So just looking at the fork, we can see that there's 2 paths, and now I've labeled the confound Z. And this is kind of what you want to do with your variables. You've got 3 variables, we want to analyze them. We've got kind of 2 paths that we can see. We've got the direct path of X to Y, that's good. We should always have X and Y in our models, like Y should be our Y variable, X should be our X, one of our X variables. But then we've also got this path through Z, because remember, if Z is, let's say Z is positive on both X and Y, if Z is large and it's maybe affecting X, so maybe it's affecting, like, for instance, your child's education or something like that, then or your grandparents' education, it's also affecting your child's education. So there's ways that it's going to affect these, and it's going to obscure this path A relationship. That's the one we really want. That's the one that we're looking for. We want the effect of X on Y, but we don't want the effects of Z on X and Y. So we need to control for it. And the easiest way to control for it, as you can probably imagine, is just, and this is the not ideal model. It's just where we have Y by X, but there's a backdoor path through Z that must be closed. So to close it, all we have to do, it's getting a bit weird, but we just add Z onto it. So if we just add Z to this model, this unknown confound, if we can measure it somehow and we can add it to the model, we've now basically closed this path. So pipes basically say that they're open, or sorry, forks just say that it's open unless you condition on Z. So again, it's open before we include it in the model, but then once we include in the model, it's closing this causal path from Z. So we're actually able to eliminate this kind of path. And another thing to note about this is that you'll note that causal paths can go upwards, upstream of arrows. It doesn't matter which way the arrow is going, they can still go upstream. So even though there's a path from X to Z to Y that we can have to worry about. And knowing that it's a fork, so just knowing that Z's in the middle and it's a fork, the rule for forks is that they're always open unless you condition upon the thing in the middle. So we have to condition upon the thing in the middle in our model. We have to add it to our model, and that closes the path. This now we're able to just measure the direct effect of X on Y without this confound Z. So just by adding to the model and understanding what a fork is, we can now eliminate the path. So we just have our path A, which is the one we want. All right. Is everyone like cool with that? This is kind of just how we do it, very roughly. But we're going to do a bunch more examples. So that's the fork. So again, we just have to condition on the thing in the middle in our model, and that will enable us to measure the direct effect of our explanatory variable on our predictor variable. Now let's go. I'm gonna have to probably restart this a bunch. Hopefully not too much. So let's go back to our initial example. Does sleep level affect student test results? So this is going to be an example of the pipe. So if we think about sleep and our test results, as that was our first kind of example, we can kind of think of it going like this: sleep and test result are Y variable on the bottom, and it's probably going to have to go through alertness in some way. So sleep level obviously is affecting alertness level. If you didn't get any sleep, you're probably not going to be very alert the next day, and alertness itself is also going to affect test level. Now, there also may be an arrow that I didn't draw here of sleep directly affecting test performance, but I honestly think that the majority of the effect, if we're thinking about student exams, would probably be through this pathway. So let's just pretend that there's just one kind of pathway here. So the first thing that we do is that we look at it and it's just one path. It's from sleep affecting alertness and then affecting test results. And there might be confounds in there, but we're not too worried about them just yet. So we've got this kind of path like this, and this is called the pipe. So the pipe, it works a lot like a fork. It goes through some middle variable, and that middle variable mediates the last one. So it's basically another way of saying this is a mediating effect of alertness. All right. So it basically is open unless you condition on the middle thing. So in this case, A is the middle thing. So if we basically include A in our model, if we include the effect of alertness, we're actually eliminating the effect of sleep on T. It's basically closed this up. So now we just have alertness affecting our test results, but we don't have any effect of sleep because it's basically blocked it. We've closed the pipe by including alertness in our model. So what you might think is like, okay, what we probably should do then is actually, and this is the graph of what it looks like if we condition on alertness, so high, medium, low. We can see that the lines are not very sloped, they're kind of flat, and that's what causes basically no effective sleep there. Obviously, this is a continuous variable, so it probably would be better if it was on a continuous scale, but I've just kind of grouped it so that you can kind of see the differences. And we saw before that when we include alertness soaks up all the variance in test result, and it basically is the main explanatory factor, and sleep does nothing essentially. But if we just stop including alertness, that mediating effect, now we have a complete picture of what's going on. Because sleep affects alertness and that affects test result, we actually don't want to condition on alertness. We don't want to include A in our model. If we include A in our model, it screws everything up. It's gonna mess it all up. It gets rid of the effect of sleep because alertness is explaining everything. But really what we're interested in is the effect of sleep on the test result. By including alertness, this is blocking it. We can't include alertness in this model. So just by doing this causal diagram, I hope you can appreciate that now we see like where we went wrong. We see that, okay, the pipe is open as you condition upon it. So by conditioning upon it, we're blocking basically the effect of sleep on test results. So we have to leave it open to see that effect. So that's one of the things about a pipe is you really have to make sure that you're leaving it all open. And then we can clearly see that sleep levels affecting test results if we just ignore the fact that alertness is also related to it. And so some of you probably noticed right away, I believe that sleep and obviously sleep and alertness are probably highly correlated. So this is one thing that multi-collinearity, or like looking at your model's collinearity, would have probably really helped. And we probably would have seen this problem right away, been like, oh, they're super related, so we should probably eliminate one. Now, just because they're collinear, that will not always be the case when it comes to causality. So we can't always rely on just using like the assumption of multi-collinearity to basically eliminate alertness. All right. And we can clearly see there's a strong effect of sleep. And I think the actual effect of sleep was exactly 1. So it's actually recovering the effect of sleep quite well once we do it. So again, this is simulated data. It's just the best kind of data to work with when you're trying to understand these systems. But obviously systems are much more complicated. But just using the simplest systems and simulating them, you can really see where problems arise very quickly. All right, so does sleep level affect student results? Obviously, yes. It's clear that we were wrong before. And modern stats might have told us include as many variables as you can, obviously without multicollinearity, but this is where we saw that we went wrong. All right, so done with that example. Does everyone kind of understand that example, hopefully? Let me know if there's any questions in the chat. All right, so we're going up to our second example, just checking the time. We're doing pretty good. I think we'll probably finish just before time. Awesome. So does basketball player height affect scoring? And notice that before we had this idea that no, there wasn't really a relationship between height and scoring ability. But it turns out that this can also be explained using a DAG, using a causal diagram. So if we did the DAG for this example, it might look something like this, where we've got height explaining scoring ability like we had before, but there's also a hidden factor that we haven't really considered in this, in that this is a subsample. This is a subset of data of just basketball players. This does not represent your everyday person. So just basketball players within this. And basically, this is essentially like a variable of like whether or not you're a professional NBA basketball player, like Michael Jordan, the greatest. And obviously, 2 things kind of go into this. If you are to become a basketball player, you're either really tall, you're really good at scoring, or you're both. And often you can be both, or you can be one or the other. So if you think of like the shortest players in the NBA, I think one's like Steve Nash. He's Canadian, so I always remember him. He's pretty short, but he's a point guard, but he's really good at other things. He's really good at blocking and things like that. And he's really good at scoring as well. And so he makes up for his height disadvantage in other ways that help the team. And so because of this, you can kind of think of basically there's 2 different things that affect it, and they collide together to determine whether or not you're a basketball player. Now, in this analysis, it's the reason why it doesn't make any sense and there's no relationship between height and scoring ability is because we've kind of conditioned on B already. And sorry, here's the paths. If we just look at the paths, there's H to S and H to B. Oop, those arrows are backwards. It should be actually going towards B, my mistake. H towards B and then S. And this is called something called the collider. The collider is a lot different from the fork and the pipe that we've seen. It's the opposite. It's always closed until you condition on the middle variable. So in this case, if we're interested in height determining scoring ability, so if height affects scoring, we might want to look at basically this extra path, this second path. But the thing is, it's closed unless we condition on Z. So that's like if we have this in our model, that would be like conditioning on B, essentially. So we don't have it in our model per se, but what we do have is basically this weird thing that if you only include a subset of B, it's essentially like you're conditioning on B itself. I'm just going to restart this. So to say it again, basically, if you have just a subset of the data and you're essentially conditioning on that variable. So this is really pertinent in terms of like survival analysis and things like that. If you have animals and they're only looking at the survivors, you have no idea of the ones that died, and that completely is changing the causal diagram because of it. So this is a huge important thing when it comes to survival analysis or anything that we've got like yes, no's. And actually it doesn't matter if it's yes, no, this could be continuous variable still, and it would still apply. If we basically only got a subset based on some criteria like surviving or making it to the NBA, then that's going to completely change our causal diagram. So by conditioning on B, this is what we had before basically when we didn't condition on B, but then once we use just the subset of data of just NBA players, we've now got another hidden relationship through B. So remember the collider says that it's closed until you condition on the middle variable, and it's colliding. You can imagine 2 arrows, they're colliding together. That's how you remember the collider. And this is the most dangerous one. This is one that is really dangerous because this is where if you add in this variable, it's going to screw up your model. Like no doubt about it. If you add in this variable, it's going to screw up your model. So in this example, there's no way, given the data we have, to do it justice. We need basically the other side of the population. We need the people who didn't make it to the NBA. We need some valid sample from them, and then we can compare them to NBA players. And you clearly see then that there's a relationship between getting in the NBA as well as height and scoring. ability. So we really are missing half the sample. And this is a really big problem in biology where extinction and things like that, even phylogenies have kind of this problem where we're making inferences based on colliders. So colliders really important as a potential backdoor path. If we're conditioning on a subset of the population, it'll completely change our results. So that's essentially what's happening here. And again, the reason why there's no relationship within basketball players is because to become a basketball player, you kind of need to be really tall, or you need to be really good at scoring, or both. So by knowing if you're a basketball player, we can basically by knowing, let's say if you were short and you were a professional basketball player, we already know that you must be really good at scoring. We already can infer extra information just by knowing kind of two of the three things. So that's how the collider effect essentially manifests. If you were really tall and you were a basketball player, we could assume that you might not be that good at scoring, but you might also be good at scoring. So we can infer a lot just from looking at the diagrams and knowing that this is a collider. All right, so there's no way to solve this one, sadly. This is one of the bad ones that we can't solve it. But there's a lot of examples of this in the literature as well. Just to highlight a few examples, the famous example of survivorship bias being the World War II planes, where they came back, they looked at where the planes that came back were shot up. And initially people thought to themselves, well, we got to reinforce these places because that will help planes survive. They're clearly getting damaged here the most. So we need to repair them here because they're obviously being, shot here the most. Just statistically, it's random. And of course, the engines lie right in this zone where they're not really shot too much. The main fuel tanks and engines. The fuel tank I think is back here actually, and where the pilot is as well is really important. So the exact opposite is true. Obviously, you don't want to reinforce the wings because the plane can get back with the wings. We're only looking at the planes that made it back. The planes that died, essentially, they were shot in all these places. The planes that didn't make it back. So this is a really good example of survivorship bias, where we just have one part of the population, one subset of the population, and it's going to affect our conclusions based on that. Another good example that just came out last month was about survivorship bias in science careers. So you see those panels all the time that tell us that I made in science by working hard, doing this, doing that. But there's actually a case of survivorship bias there, where people who are making it, they might have been lucky. They might have had like extra things. There might not actually be that much skill to making academia in the end of things. Who knows? But basically, there's a huge survivorship bias in it. In that we're only looking at part of the population. We're not looking at the part of the population that switched careers out of academia. We're looking at the people who made it in academia. So that's also a survivorship bias in there. That means that the things that they think cause them to have success might not actually be what caused them to have success. It's a kind of a biased perspective on it. All right, so survivorship bias is everywhere, super important, and it has to do with colliders usually. All right, chapter 3 is damned if you do, damned if you don't. And it's all about backdoors to hell, hence that title. So the third and final example, that's probably the most perplexing of them all, was about your grandparents' education level affecting your own. I'm doing pretty good for time. So just remembering this example, we had the grandparents, parents, and children as G, P, and C. And we saw that basically when we put in parents into the model, we had a negative effect of grandparent education level on their grandchildren's education level. So what the heck is going on with this? Well, we can try and form an initial DAG. It might look like this, where we've got grandparents affecting their children, and also grandparents affecting the parents, which affects their children. So there's kind of two different paths that we can see right here, and we're gonna have to condition on it in some way to block it. So what is this called, where we've got G to P to C with the arrows facing that way? Does anyone remember what that's called? Pop quiz. It's not a fork.
Pipe.
That's right. It was the pipe. Yes. So the pipe, if you remember the pipe, it's open unless you condition on Z. So that was the rule for the pipe. So it's basically open. It's got a light color. I tried to make it to show it's open unless you condition on the parents. So basically this path exists until you condition on P. So we actually tried both ways, remember, at the start. We tried it without and with. And when we conditioned on P, we saw that it eliminated path B by conditioning on P, closed that back door through the parents. And we just got the direct effect of grandparents on their children. Now there's also obviously an effect of grandparents through parents on their children, but we're not interested in that. We're really just interested in the direct effect of grandparents on children. And this is supposed to be C, P plus G, my mistake. C, P plus G. And when we include grandparents and parents, we saw that grandparents had a really strong negative effect. So that was where we saw the weird instance where grandparents cause a negative effect on their offspring, or on their grandchildren, I should say. So what is going on here? This is where we really need to be considerate of confounds that might exist. I'm just going to restart this quick, sorry. So one big one, oh, you probably saw everything there. One big one, we've eliminated path B, but indirectly, the way this is again simulated data, but the way it works in the real world as well is that there is this effect, and it's been shown in studies, is that there's an unknown confound that's affecting parents and children. And specifically, it's mostly because parents and children tend to live in the same households. They tend to live in the same environments. They tend to live in the same neighborhoods. And the grandparents, maybe not so much. There is cases where everyone lives together, but often it's just the parents and children together in the household. So there's this unknown confound of environment, of neighborhood, and kind of everything else that just affects parents and children. And it could also affect parents and children and obscure the relationship. So looking at this now, we've got kind of three paths from G to C. We can go G to C directly, G, P, C directly, which we've now blocked because we've conditioned on, let's say we're conditioning on parents. And then we've also got path C, which is from G to P to U to C. So my question for you now is, what is G to P to U? What is that? Do you remember what that is called in terms of what the causal alchemy is for that? It's the GPU part. If you look at that closely, you might recognize it as one of the three things I mentioned. But collider, that's right. So we've got a collider bias here. So we can see that the arrows are colliding together, and that's going to basically, if you remember the rules for collider, it's close until you condition on the middle variable. In this case, P is the middle variable. So what we've done is by conditioning on P, we've blocked path B, but we've opened a new path through this unknown confound, path C, which is probably a neighborhood effect, most likely. And by doing this, we've basically got it like this. I tried to draw a P with the kind of, it's like one and the other at the same time. We've conditioned on P in one way and blocked path B, but we've also opened up a path C now, which is even more confusing. So we've got another way that grandparents are affecting children through this unknown mediators. So we've now got a path C that we have to worry about, a causal path. So ideally, what our ideal model would look like for this is we would actually include that confound U, or that unknown neighborhood effect that affects parents and children. If we could include it in our model, then, and we can account for neighborhood effects, then we can actually eliminate it. We can close that final fork through PUC, and we'll close that. And then we just have finally the direct effect of grandparents on children. And if we do this, I just tried to exhibit this in the simulated data. It's kind of hard to plot four variables on top of each other. So the neighborhood effect is, I just divide into good and bad, like upper 50%, lower 50%, and parent level in terms of high, medium, and low as the outside rings. So we can see that neighborhoods when they're good, and parent levels when the education levels when they're high, all lead to the highest children education level. And basically in terms of grandparents, as grandparents have higher education level, it seems to affect the children's as well. But actually, if you look at the stats for this, these lines are not significant. They are zero, actually. I think the way I plotted it actually might be slightly incorrect. So the grandparent effect is null, just as I simulated it like that. I never had an effective grandparent in there whatsoever. It doesn't affect the children. And if you look at the actual effect of grandparent and children, I didn't include it on this, I forgot to, but in the test statistics, you'll see that it's basically zero. So finally, by having this ideal model of everything together, it actually does make a difference. But the problem is that we don't always know this U. We don't even know that it's there sometimes. It's really important just to think about what could be the potential unknowns or confounds in this path. So what do we do when we don't know U? Or what if we know that U's there, but we can't measure it directly? We don't know what a neighborhood effect is. What makes up a good and bad neighborhood? No idea. And we don't even know if it is just neighborhood related. It could also be environment related. There's so many possibilities here. So one thing that Richard McElrath always recommends is when you have any DEG, you just kind of try to think about all the pairwise relationships that could exist. So what kind of variables could affect this and that? Some of them are always going to be negligible. Some of them are going to be really important, such as this neighborhood effect in this case. So that's where you can kind of start, just kind of putting hypothetical unknown relationships that you might have to worry about in their paths. And they're not always going to be colliders. Sometimes they'll work out in your favor. It just depends on the diagram that you've got, the DAG you've got. So before I explain my tricks on how to deal with this unknown that we have, just want to emphasize that these backdoor effects through colliders and mediated through unknown confounds, they're everywhere in the real world. One classic example that Richard McElrath really touches upon is this effect of basically gender bias in applications. And basically, you can show this, and many papers have been written on this, that basically if you include the department effect within your model, if you include the difference in departments, you'll see that there's gender bias. And then if you remove it, there's no gender bias. So it's basically if you include it or you don't. And if you simulate this and you included the gender bias, or if you didn't include gender bias, it doesn't matter, no matter what. If you include department, it's going to change the outcome. Oops, it doesn't have it there. Hold on a sec. So basically what I'm saying is that there's no way, given the current data, to see it. If you include department, evidence of bias policing if you don't condition by department. So if you don't include department, there will be evidence of gender bias, even if there isn't. And if you do include department, if there isn't gender bias, if there was gender bias, now there won't be. So it's no matter what, you're always going to be wrong, no matter how you can do this. If you include department or you don't, you'll always be wrong. And it's because of an unknown quantity that we could call like individual quality, or basically something about that individual that makes them apply to different fields, and then affects their success or failure as well. So this is highlighted in his course a lot better than what I've just done, but basically it's almost exactly the same DAG as what we've seen before. There's this unknown quantity and there's no way to get at it. We can't know if Berkeley's hiring people or not biased, because this department effect, whether or not you include it, will completely obscure right and wrong no matter what. You can't be right. There's no way to be right unless you have more data. So the way to get around this is using the final fourth law of causal alchemy. It's the descendant, and unfortunately it's not a solve-all. It's basically we need to find proxies for these unknown quantities. So there may be a way of finding an individual's like overall academic quality in other ways, apart from just the application. There also is ways in the neighborhood effects that we might be able to gauge neighborhood effects. So that, for instance, one thing I always think of it by the Freakonomics authors, they came up with this social capital concept. I think Stephen Dubner and them and the other Stephen, social capital, which is actually can be measured by the number of bowling alleys in your neighborhood, can kind of give you an indication of how good a neighborhood is in terms of raising offspring or raising children. So we could use this kind of neighborhood proxy. And if we condition and include n in our model, we're essentially conditioning upon this u, this u, which is this fork. So by conditioning on it, we're closing it. And then we can finally explain the model again. So we need another variable just to close this up. But I think the most important thing here is not to just think about all the variables you include. It's just that if we just did it based on the variables we had, and we didn't think about it, we would have gotten completely wrong conclusions no matter what. For instance, remember when we just used grandparents alone, we got a positive effect of grandparents. When we used parents and grandparents together, we got a negative effect of grandparents. And then the actual true effect that I've programmed into it is actually 0. There's no effect of grandparents directly on children. This blue line is 0. But if we just did it willy-nilly and we didn't think about this, we would have always gotten the wrong answer, and it would have been horribly wrong either way. And we would have had a paper. We would have written a paper and it would have been incredible. Grandparents have negative effects on children. And it would have, got accepted into science maybe, probably not, but one can hope. And we would have made these completely wrong conclusions. But making these causal diagrams really helps to elucidate what could be out there, what are the backdoor pathways from our X variable to our Y variable. And I think that's why I'm stressing it's so important. So just as a final takeaway, as I'm pretty much done after this. So some things I talk about: use experimental design to eliminate the influence of external confounds, these exogenous confounds, and just try and be as controlled as possible. But when you can't, and a lot of times you can't, in everything field-based, usually it's very hard to eliminate everything from the environment. We have to rely on kind of causal assumptions. So we have to use these DAGs, these directed acyclic graphs, to form assumptions about your system, no matter how complicated, just to get some idea of what's going on. And again, you will never be perfect with this. It's always kind of, you're guessing, but you're making educated guesses. You're using science that you're using your knowledge of the system to make these assumptions, to make these guesses. And you can test different ones as well. There are ways that he goes through in his course that you can actually test multiple causal diagrams and see which one's best. So for instance, when you can't know whether a confound is occurring, you can use kind of assumptions about the confound, how strong it might be relative to other subjects or other variables. And we can use things like structural equation modeling or path analysis to analyze this. And then in more advanced cases, Bayesian networks, or as Richard McElrath likes to say, full luxury Bayesian inference, because it's fancy, but it's computationally expensive, and it requires a lot of forethought about it. And there's a little bit of math in there too that you have to worry about. So there are ways of dealing with it, but they're going to ever get more complicated in terms of what you're dealing with when you don't know the unknown confounds that you think are there. But these can be used to estimate unknown or latent parameters, and there will be some uncertainty to them, but at least now you've got the idea of what it could be within the realm of possibility. You've got kind of it pinned down a little bit better than what you had before. It's much better than ignoring these confounds. If you don't deal with them, that's when you can really have issues, especially if they're kind of somewhat well-known confounds. So you'll never get every confound, and I'm not saying go out and do every single possible latent variable you can, but I am saying that you need to consider the ones that might be within the realm of possibility when you're doing science, and try and understand how they'll affect your statistical models. So it's never going to be perfect, but we always strive for better. And as you've seen, it's you're damned if you do, damned if you don't sometimes, including variables, but at least causal diagrams can show you why that might be happening, why the whole results can change when you do this. And you can even simulate it. It's really easy to simulate, I found out when I was doing this talk. So thanks again, everyone, for listening today. Please check out Richard McElrath, who's again, I didn't steal, but I borrowed a lot of what he said on YouTube and through his lectures. So thanks. I just have to extend my gratitude towards him for doing all this kind of free stuff for the community in stats and explaining it so well. I couldn't do this talk without how well he's explained it. He has a whole course that you can actually go through on YouTube. He also has this statistical rethinking book that you can go through. I think there's ways of getting free ones around it. I won't promote free copies, but it's an amazing book. If you do want a book, it's like the only main stats book I'd recommend. It's all about using Bayesian stats, but it's really easy and accessible. He's got his own R package as well. I'm just plugging Richard McElrath here, but yeah, highly recommend watching these YouTube videos just for starters, because it will really unmask the idea that we are always so wrong, and we have no idea how wrong we are. And even as scientists, even as statistical modelers, we're actually often more wrong than right. And I think accepting it is just the first step in getting anywhere. All right, and that's everything. Thanks everyone for listening.
Thank you, Kevin. That was amazing.
Sorry
a lot of information.
Yeah, sorry for my ranting and everything. But if anyone has any questions, let me know.
No questions here, but that's awesome, Kevin. Cheers.
You go, Kens.
No, I don't. Does anybody have any questions? No. I just want to say, Kevin, that was awesome. Yeah, super helpful, and yeah, maybe some of my papers should be published.
No, I'm sure it's fine. It's all right. You can do like a response to your own paper. Just kidding.
Kevin, I have a question for you. That was really great. So you would use this in line with Bayesian statistics as opposed to frequentist, or
so
can you use with either?
Yeah, it can be used with either. The way I understand it, and I'm not an expert on SEM or structural equation modeling by any instance, but I think structural equation modeling is more the deterministic or frequentist way of doing it, from what I understand. Maybe Alfonso can correct me. And then Bayesian networks are kind of like the Bayesian way of doing it. There's kind of advantages to both. There's more advantages to Bayesian inference for sure in terms of interpretation at the end. And actually, yeah, Alfonso keeps shaking his head, but there's a lot to be.
No, that's right.
He's very passionate about this. He's better explaining why confidence intervals are completely wrong in frequentist stats. But that wasn't the issue with that wasn't the main point of my talk. It wasn't to promote them, but actually, Richard McElrath always says it's not about frequentist and Bayesian. It's actually more about these causal diagrams than anything else. He always points out that yes, they're different tools, but they should come to the same conclusions if they're built obviously the same. They should really come to similar conclusions. Alfonso says no, but in general, in simpler cases, they should come to the same conclusions. But really what's important is what you base the model on in the first place, which should be kind of causal diagrams, these DAGs, if you can. And obviously, DAGs get really complicated often, but if you're trying to imply causation about something causes something else, rather than dedicating a whole paragraph to your discussion about this weird influence that you found, it might be worth considering why that occurred in other ways, like unknown confounds as well. Yeah.
Cool, thanks. And so this is something you would do before even running a model, you would be creating
I mean,
these DAGs, right?
I'm just new to this, so I've tried.
Mm.
I've started doing it. I'm helping Tess with some stuff, and I made a DAG for her stuff. So, but yeah, it is like new to me too. It's new to kind of everyone in biology. I think we never really talk about this, but it's so important.
Oh.
And the fact that we don't talk about it is just appalling to me. That everything can be wrong if we aren't careful. So yeah, I'm going to start doing it more. I haven't
cool.
in the past, but I'm sure I've also got papers that need to be retracted. I know that I've got one that's terrible. Yeah.
Well, you know.
Probably terrible for my honors, but it's done, so I can't go back.
It's all right. We don't have to go there, but cool. Thanks, Kevin. It was super cool.
Thanks,
Yeah, that was awesome. So I have questions. So if you've got a collider, you basically can't fix it unless you get more data. Is that what you're saying?
Yeah, so colliders through the survivorship bias, yes, but often you have you can get a proxy, remember, so you can get like a proxy variable. So maybe you have some way of controlling for who made it to the NBA. So maybe you have a continuous variable that is indicative of it. So maybe you could get someone scoring on NBA tryouts and like their score and include that as like a proxy for whether or not you're in the NBA. So then in that way, you're using the descendant to condition upon that and get closer to the truth.
Okay.
And
so when you say, sorry, carry on.
I was just gonna say colliders don't have to be like yet survival necessarily. They can also be continuous variable. It's just in the case you often see them in survivorship bias because you've got, yes, you survived, but you didn't. But yeah.
Yeah, okay. And so when you say condition for and including whatever Z or U in your model, this is as a variable or as a covariate, or it doesn't matter, or?
Yeah, it's a good point. So you just basically need to include it in some way in your model. So or don't in the case of a collider. So in the case of collider, you probably actually wouldn't want to condition on the descendant. My bad. But yeah, basically, if you do a subset of data, that's kind of like conditioning on it. It's basically like you're considering only one of the groups in that factor, if you will. Obviously, kind of everything's in a continuum in a way, but for strict cutoffs like the NBA or survival, there's you live or you don't. So in that case, it's a group variable, but it doesn't have to be. It can also be a continuous variable. It just depends on the system. So you can have colliders with continuous variables as well. Yeah.
Yeah. Okay. And my last question is, if you're doing field stuff, how do you ever trust what you find? Like, we know that I don't like stats and I'm not confident in it, but I feel like this has just ruined any potential confidence I might have. What you're saying is anything I do could potentially be wrong if there is some confounding factor that I haven't thought about. And if my stuff is field, there could be a million confounding factors.
Of course. I think it's important to just keep focus. I mean, yes, you could have a million random crazy butterfly effect ways that something affects something else, but I think it's just be reasonable about what could affect something. It's really only a major issue when there's like major confounds. I know that there's a lot of stuff that's kind of linked together, like in terms of physiology, when things are like super correlated, like pathways very, very correlated together. Often what they do for that is you can actually treat some things that are super correlated together as just like one variable essentially, and then other parts of the system as again one variable. So if you can lump it that way, you're always going to be making causal assumptions in your models, and you're always going to be wrong in some way. You can never be right. Richard McGowan always just says like, just try your best. It's better than not trying at all. So just don't, and it's discussion points. It's more part of your discussion if you've got some possible confound here. But although they're everywhere, like they don't have often as strong of an effect as the main effects. And if you manipulate it, it's more likely than not that your manipulation's the thing that's causing it if you do something in that field. Yeah.
Yeah. Okay. Awesome. Thank you.
Have faith. There is still something there that's always publishable. It's just a lot more complicated than we think of it usually. And none of these ideas are mine. As I mentioned, so I know you're trusting me in my judgment, but I also don't really know. I'm still like new to this stuff. So I strongly recommend checking out his course, watching it over lunch break if you can for the next week. And it's really good to explain things. Yeah. Anyway.
That was really good, Kevin. That's great. Really enjoyed it. Do you have any idea about the extent of like these errors within the scientific community? Anything like that?
Yeah, like I think they're like all over the place. They're really apparent, like where they really get you is in like psychology studies, because humans are really inherently complicated. But I can even think in terms of like health studies. Me and Suze have talked about like the effect of certain diets and things. A lot of problems with like health studies that are observational is that they'll basically people who are eating a certain food will tend to be healthier, have lower instances of cancer. But the problem is the people who are looking for this information about health foods are also already healthy because they're trying to be healthy. Whereas people who aren't super healthy are not ever going to come across these foods. So there's already a bias there. And I haven't made up the causal diagram, but that would also affect it. So you've already got some biases in terms of the population right there. So obviously the ones that are healthy, they're always going to stay healthy. And even if the food has no effect, they're going to think it does, and they're already healthy. So this study will show that essentially an observational effect that this thing is promoting health, but it's not actually.
Yeah, I saw an interesting example the other day from vaccine effectiveness. So they did these efficacy trials, and you can do that in a randomized control study, right? Sort of use randomization to establish causation. But then when they start doing effectiveness in the real world, there's a bunch of data sets that have sort of come out that have Simpson's paradoxes in them, where it's sort of age, because the vaccination efficacy changes depending on age group. So you end up with these like negative correlations, and it looks like the vaccines aren't working, but they're actually like but yeah, seems like it's everywhere. It
is everywhere. And I think, first step is accepting it, that we're all wrong.
We all have to stand up and say, I am a statistician.
It's a way of thinking about things, but don't change anything you're necessarily doing, just consider it. But apparently teenage pregnancy was largely dropped off in the States because of 18 and Pregnant, or whatever that show was, 16 and Pregnant. Apparently that had a huge popular culture influence on the rate of teenage pregnancies. And after that show debuted, the rate of teenage pregnancies after 9 months of that show debuting dropped incredibly fast, just because of that one show. Anyway, random tidbit of information, I know. But anyway, if there aren't any questions.
I've just thought of one more. So you know how you've got your arrows in your decks, like how do you work out which way it's going and therefore which type of model is? So for example, I'm looking at coral stuff, and a lot of coral biology is dictated by size, but size is not age. It's they're not strictly related. So like how do you, like size could affect the factors that I'm looking at, but size itself is also going to be affected by other things. So like, how do you begin to work out which way the arrows are going?
I guess then you might have to divide up in terms of, you could either divide it up in terms of different processes, like maybe it's affecting a process that wasn't measured, that you know of, that would affect the other variable. And then that it goes back to, well, I guess it can't be looping is the issue. If something's highly correlated, often what they do is they just lump it together. So if you do have two things strongly related, like age and size, you might be able to just put it into one kind of category, and do it with that, and just see which one's a better predictor at the end. So you don't include both of them in your model, but because they're obviously collinear and correlated anyway. But
okay, so for an example of what I'm looking at is competition. So competition could affect size, but size could also affect competition, as in if it's a bigger colony, it's more likely to be competing because it will meet more people. So how do I work out which way that arrow is going?
So competition affects size because it's growing, or sorry, size affects competition because it's growing faster and meeting more individuals. And then
but competition can affect size because if it's being competed against, it may not have the capacity to grow and flourish.
So I would be tempted to look at like partial mortality due to competition would be like one of the processes that you could divide one of them into to get back at that.
So is that adding a descendant or whatever it is and using, is that?
Yeah, I think so. It's honestly, it's never, so I showed a bunch of examples. It's never that straightforward though. And these DAGs can get intense. And I think Wicham was telling me once, he had to leave, but he was telling me a couple of weeks ago about how he's trying to design these phylogenetic DAGs, and they're extremely complicated. But yeah, so it's not going to be a one size fit all. I guess there's, you just have to start by like trying to guess at what's there and the processes. And so maybe if you've got partial mortality on one end, you might have like incidents of meeting new individuals on the other end. But yeah, I'm sorry, I'm not good at on the spot of thinking of these things.
No, that's fine. I don't know how you begin to work out. Like I can see the different factors that might affect it, but how on earth do you begin to work out which way and how it all connects? But I guess that's just practice and experience, right?
Yeah. So speaking from corals, the way I always use Josh Madden's paper for partial mortality, where it's got this is not related to anyone's work, but where it's got growth balanced with partial mortality, and they estimate like a maximum growth, and then whatever they don't grow relative to maximum growth, they call that partial mortality. So there might be a way of like modeling it that way. It's more like a demographic way.
Yeah, okay.
You check out his 2019 or 2020 paper.
Okay, awesome. Thank you.
Anyway, yeah, as we've just seen, I'm no expert. Anyway, thanks everyone for listening. I won't hold you any longer.
Kevin, that was really good.
It was awesome. Thank you again.
Yeah, thank you. Yeah.
Are we starting the course next week?
So it's not next week. We were going to have like a pause because we're having the conference, the CTBMB conference that Ira is running in Mission Beach. So Legana and I, we will present there a little bit what the club is doing. So if you guys want to like us to tell something about the club, let us know. And then we were thinking of starting the beginners course again. So depending on how that goes, we will see if we are going to do it every session or every other session, right? That was the plan.
Mm-hmm. Yeah.
So if any of you wants to sign up to do one of these sessions, let us know and we will send you. I mean, I think that the link is in the, let me check, in the Google Docs. Is there, Kevin, in the Google Docs?
Yeah, it is. I'm just trying to find it. Let's go to it. It's this software company course called R for Reproducible Science. It's if you've done anything in R, you'll probably be able to present a chapter if anyone's interested. This is where we're just trying to recruit kind of new members throughout these talks. Because although we've got all these experts in R, it seems like here, we also need to educate kind of like the next generation. So. And yes, there's mugs left. Does anyone not have a mug at this point?
Never collected mine yet.
Oh, okay. I'll bring it one time to you. I've got some of the mugs, but I'm running out. Ira has the rest of them. But yeah.
I can give it to you, Tessita. I can ask Ira. But which color do you want? Green?
I didn't know there was an option. I'll leave it to you to choose.
There is blue and green, right? Which ones do you have, Kevin?
I have blue. Yeah.
Blue.
There's like 5 blue ones left. Now the green ones are all exclusive because no one has a green. Yeah.
Oh, okay.
Yeah.
We're gonna go. Catch you later. Thanks, Kevin.
Okay, thank you. Thank you. Bye.
Okay,
I will put the link in the chat just in case anybody wants to have a look of the software carpentry one.
Cool.
And if you can sign up, please do it so we don't have to run all the sessions. Thank you. And so pause the next Monday unless someone wants to present, and then we start on the 8th, if I'm not wrong, of November.
Martina I think Martina said she wants to present next week.
Does she?
Yeah, I think so. Oh yeah, I'm actually not even.
I think she's hiding.
Martina, she's in the other room.
Okay.
I gotta go.
Well,
anyway,
thank you everyone. Thank you, Kevin.
Thank you. See ya.
Bye bye.